What scientists found inside a black hole changed physics forever. For 100 years, they lurked in the darkness. Monsters so powerful, they devour light itself. We've photographed galaxies billions of light years away. We've captured the birth of stars and the death of solar systems. But there was one cosmic beast that always escaped our lens. These cosmic monsters have been hiding in plain sight, controlling the destiny of entire galaxies while remaining invisible to our most powerful telescopes. April 10, 2019, 6 press conferences, 3 continents, 1 image that would change our understanding of the universe forever. The culmination of a century of theoretical physics, decades of technological advancement, and an unprecedented collaboration across our planet. In conference halls across the world, hundreds of journalists waited. Scientists made their final preparations. Years of work, millions of dollars, and countless sleepless nights, all leading to this moment. Behind closed doors, teams were running final checks on presentations that would reveal humanity's first glimpse of a black hole. The journey to this moment began over a century ago. In 1915, our understanding of the universe fundamentally changed. General relativity revealed that space and time themselves could bend and warp. In the corners of these equations lurked something that seemed impossible, regions where gravity becomes so intense that nothing could escape, not even light itself. Imagine space and time as a vast cosmic fabric. Now picture a bowling ball placed on this fabric, creating a deep depression. A black hole is like an infinite well in this fabric, so deep that anything that falls in can never climb back out. Even light, the fastest thing in the universe, once past a certain point, can never escape. For decades, these cosmic monsters existed only in mathematical equations. The first solution came from unexpected quarters. A physicist serving on the Russian front during World War I, working in between artillery barrages, he discovered the mathematical blueprint for what we now call black holes. As technology advanced, astronomers began hunting for these invisible giants. They watched stars dance around unseen partners. They measured gravitational waves rippling through space. They mapped vast regions of darkness at the hearts of galaxies. But seeing a black hole directly? That seemed beyond human capability. The challenge was immense. Imagine trying to photograph a black cat in a coal mine from thousands of miles away. Now make that cat smaller than an atom, and the mine the size of our solar system. That's what these scientists were attempting. The solution? Turn our entire planet into one giant telescope. 8 observatories across 4 continents, from the snow-capped peaks of Hawaii to the high-altitude deserts of Chile. Each facility precisely synchronized using atomic clocks accurate to within a fraction of a second. But nature itself seemed to conspire against success. At these frequencies, water vapor in Earth's atmosphere acts like a cosmic fog bank. Each telescope needed perfect weather conditions simultaneously. The odds were astronomical. When everything aligned, the data poured in, each telescope generating so much information that it couldn't be transmitted electronically. Hard drives had to be physically shipped to processing centers. In 1 week of observation, they collected more data than the entire Library of Congress. Processing this tsunami of information required new kinds of algorithms. Traditional imaging techniques couldn't handle the complexity. Teams developed artificial intelligence systems that could fill in the gaps, cross-reference millions of data points, and gradually build up an image of something that had never been seen before. As the image slowly emerged from the noise, excitement built. The theoretical predictions were being confirmed 1 pixel at a time. The distinctive ring structure, the asymmetric brightness, the central darkness. All exactly as Einstein's equations had predicted a century earlier. After months of verification, double-checking, and peer review, the moment of revelation arrived. As screens lit up across the globe, humanity collectively held its breath. For the first time, we were about to see what had previously existed only in equations and imagination. There it was, a glowing ring of light surrounding an abyss of darkness. The point of no return made visible. A window into the most extreme environment in the cosmos where our understanding of physics breaks down completely. This wasn't just a photograph, it was the culmination of human curiosity and determination, a testament to what we can achieve when we push beyond what seems possible. The image revealed not just a black hole, but the power of human collaboration and ingenuity. But this was just the beginning. With this breakthrough, a new era of black hole astronomy began. Questions that had puzzled scientists for decades could now be investigated directly. The image opened a new window into the most mysterious objects in our universe. This is the story of the impossible photo. And it begins with a simple question: how do you photograph something that eats light itself? Time, a concept we thought we understood until Einstein came along. In a patent office in Bern, Switzerland, a young clerk was about to turn our understanding of the universe upside down. The year was 1905, and Albert Einstein was about to begin a journey that would lead us to the most extraordinary prediction in scientific history. It started with a simple thought: what would happen if you could chase a beam of light? This childlike question would eventually reshape our understanding of space, time, and gravity itself. But Einstein's most haunting prediction was yet to come. By 1915, Einstein had completed his masterwork, the theory of general relativity. Hidden in these equations was something so bizarre, so contrary to common sense, that Einstein himself refused to believe it could exist. The mathematics suggested regions of space where gravity became so powerful that nothing could escape, not even light itself. For years, Einstein tried to prove these dark stars couldn't exist. But the mathematics was uncompromising. The same equations that perfectly explained the orbit of Mercury and the bending of starlight also predicted these cosmic monsters. The term black hole wouldn't be coined for another half-century, but their shadow already loomed over physics. Other scientists began taking these predictions seriously. In 1916, Karl Schwarzschild, while serving on the Russian front in World War I, found the first mathematical solution describing these objects. Between artillery barrages, he worked out the exact geometry of space around what we now call a black hole. Weeks after publishing his solution, Schwarzschild died at the front, never knowing how his work would revolutionize our understanding of the universe. The decades that followed saw a parade of brilliant minds wrestling with these cosmic enigmas. In the 1930s, young Indian scientist Subramanian Chandrasekhar calculated that some dying stars must inevitably collapse into black holes. The distinguished astronomer Arthur Eddington dismissed his work as mathematical nonsense. Chandrasekhar was right, but it would take decades for the scientific community to accept it. By the 1960s, theoretical evidence for black holes was mounting. Mathematicians discovered that every black hole, regardless of what formed it, would eventually settle into a simple state defined by just three numbers: mass, spin, and electric charge. Everything else about the original object would be erased, lost forever behind the event horizon. The first indirect evidence came from an unexpected source: X-ray astronomy. In 1964, scientists launched detectors aboard rockets that discovered intense X-ray sources in space. One, called Cygnus X-1, seemed to be powered by matter falling into a black hole. But seeing was believing, and no one had ever seen a black hole. The challenge seemed insurmountable. How do you photograph something defined by its inability to be seen? Early attempts focused on the wrong wavelengths, used insufficient telescopes, or simply lacked the technology to process the vast amounts of data needed. In the 1970s, astronomers realized that black holes might be visible not by their darkness, but by their effect on nearby matter. As gas and dust fall toward a black hole, they form a swirling disk of material heated to millions of degrees. This glowing disk, combined with the black hole's intense gravity bending light around it, should create a distinctive ring-like image, a shadow of the black hole itself. But capturing this shadow would require a telescope the size of Earth. The resolution needed was equivalent to reading a newspaper in New York from a sidewalk cafe in Paris. For decades, this seemed like an impossible dream. Then came a breakthrough. Radio astronomers developed a technique called Very Long Baseline Interferometry, VLBI. By combining data from multiple telescopes spread across the globe, they could simulate a telescope as large as the distance between them. Suddenly, the impossible seemed merely extremely difficult. The first serious attempts to photograph a black hole began in the 1990s. Each failure taught valuable lessons. The technology wasn't quite there yet, but with each passing year, computers became more powerful, algorithms more sophisticated, and our understanding of black holes more complete. Meanwhile, theoretical physicists continued making predictions. They used supercomputers to simulate what a black hole should look like when finally photographed. These simulations would prove crucial when the real image finally arrived. As the new millennium dawned, the pieces began falling into place. Atomic clocks became accurate enough to synchronize telescopes across continents. Computer storage could handle the massive amounts of data required, and a new generation of scientists emerged, determined to achieve what their predecessors had thought impossible. The stage was set for one of the greatest scientific endeavors in human history. But first, they needed to choose their target. Which black hole would finally reveal its face to humanity? This is where our journey through time meets the present, and where the real work of photographing the impossible began. Science fiction has always dreamed of black holes. From the pages of novels to the silver screen, these cosmic monsters have captured our imagination. But how close did Hollywood come to reality? The answer would surprise even the most imaginative filmmakers. Before we saw the real thing, black holes lived in our collective imagination. They were portrayed as cosmic whirlpools, galactic vacuum cleaners, or portals to other dimensions. Each representation reflected our fears and fascinations about these mysterious objects. In 1979, Disney's The Black Hole introduced mainstream audiences to these cosmic phenomena. The film's depiction was more fantasy than science, a swirling vortex of blue light leading to unknown realms. While scientifically inaccurate, it captured the public's imagination and sparked interest in these mysterious cosmic objects. Then came Stephen Hawking's A Brief History of Time in 1988, changing how we communicated black hole science to the public. Suddenly, complex physics concepts were accessible to everyone. Artists and filmmakers began consulting scientists, trying to bridge the gap between imagination and reality. By the 1990s, documentaries and science programs were using computer graphics to show black holes warping space-time. These visualizations, while simplified, helped the public understand Einstein's complex ideas about gravity and space-time curvature. In 2000s, Disney tried again with Mission to Mars, featuring a more scientifically informed depiction. The film showed the effects of immense gravitational forces and time dilation concepts straight from Einstein's equations. While still taking creative liberties, it marked a shift toward more scientifically accurate portrayals. But it was Christopher Nolan's Interstellar in 2014 that revolutionized how we visualize black holes. The film's visual effects team worked with theoretical physicist Kip Thorne to create Gargantua, the most scientifically accurate black hole visualization ever seen in cinema. They wrote new rendering software to accurately simulate gravitational lensing, accretion disks, and relativistic effects. The result was stunning. Gargantua showed how light would actually bend around a black hole, creating the distinctive asymmetric brightness that we would later see in the real image. The film's portrayal was so accurate that it led to scientific papers about black hole visualization. Yet even Interstellar had to make compromises. The accretion disk was brightened to be visible on screen. The subtle details of gravitational lensing were exaggerated for dramatic effect. Reality, as we would discover, had its own dramatic flair. Television documentaries continued evolving their representations. Computer animations became more sophisticated, incorporating the latest scientific understanding. Each new visualization brought us closer to what we might actually see when we finally photographed a real black hole. Science programming faced a unique challenge: how to explain something that defies everyday experience? They developed clever analogies: rubber sheets representing space-time, marbles showing orbital paths, whirlpools demonstrating gravitational pull. These metaphors, while imperfect, helped viewers grasp fundamental concepts. As we entered the 2010s, scientific visualization software became increasingly powerful. Astronomers could create highly detailed simulations of black hole environments. These simulations would prove crucial in understanding what we were seeing when the real image finally arrived. Online educational content exploded with black hole visualizations. YouTube channels and educational websites competed to create the most compelling and accurate representations. Some came remarkably close to predicting what we would eventually see. Video games joined in with titles like Elite Dangerous and Space Engine, incorporating scientifically accurate black hole physics. Gamers could experience gravitational lensing and relativistic effects in interactive environments, building intuition about these complex phenomena. Then came April 10, 2019. The real image was revealed, and something remarkable happened. Reality proved stranger than fiction. The actual photograph showed features that even the most sophisticated Hollywood visualizations hadn't captured perfectly. The asymmetric brightness of the accretion disk, the precise way light bent around the event horizon, the subtle details of the black hole's shadow, these elements had their own elegant beauty that no artist had quite managed to reproduce. Hollywood had imagined black holes as violent, dramatic objects. The reality was more subtle but no less spectacular. The real image showed a quiet majesty, a silent sentinel at the heart of a galaxy, bending light into a perfect ring of fire. The entertainment industry immediately began incorporating the real image into their productions. Documentaries were updated, visual effects were refined, and new projects were launched incorporating our new understanding of what black holes actually look like. This marked a new era in the relationship between science and entertainment. No longer did artists need to guess what a black hole might look like. They had reality as their guide. But this didn't constrain creativity. Instead, it provided a foundation for even more imaginative explorations of these cosmic wonders. The real image also validated many of the scientific principles that entertainment had tried to convey. Concepts like gravitational lensing and relativistic effects, once seemingly abstract, were now visibly demonstrated in nature. Today, as we continue capturing more detailed images of black holes, science and entertainment continue their dance. Each new discovery provides inspiration for artists and filmmakers, while creative visualizations help scientists communicate their findings to the public. What began as pure speculation in the minds of science fiction writers has become observable reality. But rather than diminishing the mystery of black holes, Seeing them has only deepened our sense of wonder. Behind every great scientific discovery are the dreamers, those who dared to imagine the impossible. The story of photographing a black hole isn't just about technology and physics. It's about the human spirit of exploration and the remarkable individuals who made it happen. This journey begins with a young graduate student who asks a simple question: what if we could see what happens to matter as it falls into a black hole? That question would eventually grow into a global collaboration involving hundreds of scientists, but it started with just a handful of dreamers. Every morning for years, Shep Dulleman would arrive at his office with a seemingly impossible goal. His colleagues called it crazy, trying to photograph something that swallows light itself. But Dulleman knew something they didn't. If you gather enough telescopes, synchronize them perfectly, and process the data just right, you might catch a glimpse of a black hole's shadow. In the basement of a physics building, Katie Booman was tackling a different challenge. How do you create an image from incomplete data? Traditional imaging techniques wouldn't work. She developed new algorithms that could piece together fragmentary information, like solving a puzzle with most of the pieces missing. Across the ocean, Heino Falca had been preparing for this moment since childhood. Growing up in post-war Germany, he would look at the stars and wonder about the mysteries they held. Decades later, he would help convince the scientific community that photographing a black hole wasn't just possible, it was necessary. In Japan, Mareki Hanma was perfecting the art of linking telescopes. His work on radio interferometry would prove crucial in transforming multiple telescopes into a single Earth-sized observatory. Each technical breakthrough brought them closer to their goal. The team grew. Young researchers joined veterans. Graduate students worked alongside Nobel laureates. What united them was a shared vision, to see what had never been seen before. They came from different backgrounds, spoke different languages, held different beliefs. But they shared a common language: mathematics, physics, astronomy. In control rooms and conference halls, they worked to overcome not just technical challenges, but cultural and linguistic barriers. Late nights merged into early mornings. Holidays were spent calibrating equipment. Weekends disappeared into data analysis. Their families learned to understand that when you're chasing the impossible, normal schedules don't apply. Some sacrificed promising careers in other fields. Others spent years away from home, stationed at remote observatories. Many missed important life events, working through birthdays, anniversaries, and celebrations. The pressure was immense. The world scientific community was watching. Funding agencies wanted results. Critics said they were wasting time and resources. But the dreamers kept dreaming, kept working, kept pushing forward. They celebrated small victories: a successful telescope synchronization, a breakthrough in data processing, a promising test result. Each step forward renewed their commitment, reinforced their belief that they were on the right path. Young researchers brought fresh perspectives. They questioned established methods, proposed unconventional solutions, saw patterns that others missed. Their energy and optimism balanced the cautious wisdom of experienced scientists. In remote observatories, technicians worked in extreme conditions. At high altitudes, where the thin air made every task more challenging, they maintained complex equipment in sub-zero temperatures. Their dedication was as crucial as any theoretical breakthrough. Computer scientists wrote millions of lines of code. Engineers designed new hardware. Mathematicians developed novel theories. Each contribution was a thread in a larger tapestry, weaving together to create something unprecedented. The team faced setbacks. Equipment malfunctioned. Weather conditions destroyed observation windows. Promising approaches led to dead ends. But after each failure, they regrouped, learned, adapted, and continued. They found support in unexpected places. Local communities near observatories embraced the project. Universities provided resources. Students volunteered their time. The dream of seeing a black hole had become a shared human endeavor. As data began flowing in, excitement built. The first hints of success emerged from the noise. Preliminary results suggested they were on the right track. The impossible was becoming possible. The team grew more diverse. Scientists from developing nations brought new perspectives. Women in leadership roles challenged traditional hierarchies. Young researchers from underrepresented communities brought fresh energy and ideas. They shared their journey with the public. Through lectures, interviews, and social media, they made complex science accessible. They inspired a new generation to dream big, to pursue the impossible. When the final image emerged, it wasn't just a scientific triumph. It was a human one. It represented thousands of individual stories, countless personal sacrifices, and unwavering determination. These dreamers had achieved something remarkable. They had pushed the boundaries of human knowledge and capability. But more than that, they had shown what people can achieve when united by a common goal. Their legacy isn't just the image they captured. It's the example they set, the barriers they broke, the possibilities they opened. They showed that with enough dedication, collaboration, and imagination, even the most impossible dreams can become reality. To understand the magnitude of photographing a black hole, we need to grasp the astronomical scale of the challenge. Imagine trying to spot a grape on the moon from Earth. Now make that grape billions of times farther away and make it invisible. That's what these scientists were attempting. The target was Messier 87, a supermassive black hole lurking 55 million light-years from Earth. Its mass is equivalent to 6.5 billion suns compressed into a space smaller than our solar system. The gravitational pull is so intense that it distorts space-time itself, creating a perfect prism for light. The size of this monster defies comprehension. You could fit our entire solar system inside it with room to spare. Yet from Earth, it appears smaller than a single grain of sand viewed from a mile away. This presents the first major challenge: resolution. Traditional telescopes, even the most powerful ones, couldn't capture enough detail. The required resolution would be equivalent to reading today's newspaper headlines from New York while sitting in a cafe in Paris. No single telescope on Earth could achieve this. Then there's the distance problem. At 55 million light-years away, the light reaching Earth is incredibly faint. Most of it gets scattered or absorbed by our atmosphere. The signals are so weak that detecting them is like trying to hear a whisper from across the ocean. The black hole's environment presents its own challenges. Surrounding it is a maelstrom of superheated gas, swirling at near light speed. This creates a constantly changing environment that distorts our view. It's like trying to take a clear photograph through a heat wave. Temperature variations in Earth's atmosphere create additional distortions. Even minor atmospheric fluctuations can blur the image. The effect is similar to the twinkling of stars, but at a much more problematic scale for our observations. Time itself becomes a challenge. Because of the vast distances involved, the light we capture left its source millions of years ago. We're not seeing the black hole as it is now, but as it was when dinosaurs still roamed Earth. Any changes happening now won't be visible for millions of years. The rotation of Earth compounds these difficulties. As our planet turns, telescopes move relative to the target. This means observations must be precisely timed and coordinated across multiple locations to create a coherent image. The sheer volume of data presents another massive hurdle. Each telescope generates petabytes of information, millions of gigabytes, that must be processed, synchronized, and combined. It's like trying to combine millions of jigsaw puzzles, where each puzzle shows only a tiny part of the picture. Weather becomes a critical factor. All participating telescopes need clear skies simultaneously. Given that these observatories are spread across different continents and climate zones, achieving perfect conditions at all locations simultaneously is extremely rare. The technical precision required is mind-boggling. Atomic clocks at each telescope location must be synchronized to within a fraction of a second. Even a tiny timing error could blur or distort the final image. Each telescope must maintain incredibly precise pointing accuracy. The slightest vibration, even from wind or distant earthquakes, could throw off the observations. It's like trying to hold a laser pointer perfectly steady on a target thousands of miles away. The energy reaching our telescopes is incredibly weak. The total amount of energy received from the black hole during the entire observation period is less than the energy of a single snowflake hitting the ground. Detecting such faint signals requires extraordinary sensitivity. Then there's the challenge of interference. Radio signals from cell phones, satellites, and other human activities can overwhelm the faint signals from space. Each observatory must carefully filter out this noise while preserving the precious data they're seeking. The computer processing requirements are enormous. Traditional imaging techniques weren't sufficient. New algorithms had to be developed that could reconstruct an image from incomplete data, like trying to create a photograph from random pieces of different pictures. The margin for error is incredibly small. Even minor miscalculations or equipment malfunctions could render entire observation sessions useless. Every component must work perfectly, often for extended periods. At high altitudes where many telescopes are located, thin air makes maintenance and operation challenging. Technicians must work in harsh conditions, often with limited oxygen, to keep equipment running perfectly. Finally, there's the fundamental paradox of the task itself, trying to photograph something that, by definition, cannot be photographed directly. We can only see its effect on the space and matter around it, like trying to photograph wind by watching leaves move. This combination of challenges made the task seem impossible, yet understanding the scale of these difficulties was crucial to developing solutions. Each challenge required innovative thinking, new technologies, and unprecedented collaboration. How do you build a telescope the size of Earth? The answer lies in one of the most ambitious scientific collaborations ever attempted, the Event Horizon Telescope project. This isn't just one telescope, it's a network of observatories working together as a single planet-sized instrument. The concept sounds deceptively simple. Place radio telescopes at different points around the globe, then combine their observations. But achieving this required pushing technology to its absolute limits and inventing new solutions where existing ones fell short. Each telescope in the network is a marvel of engineering. These aren't ordinary radio dishes. They're highly specialized instruments capable of detecting incredibly faint signals from space. The surfaces must be perfect to within a fraction of a millimeter, despite spanning dozens of meters in diameter. The locations were chosen with extraordinary care. Each site needed specific characteristics: high altitude to get above much of Earth's atmosphere, stable weather patterns, and infrastructure to support complex scientific equipment. But they also needed to be spread across the globe in a precise pattern. At the summit of Mauna Kea in Hawaii, technicians worked in thin air at nearly 14,000 feet. In the Atacama Desert of Chile, engineers battled extreme temperature swings and bone-dry conditions. On the high plateaus of Mexico, teams coordinated observations through tropical weather patterns. Synchronization became the greatest challenge. Each telescope needed to know the exact time to within a fraction of a billionth of a second. Atomic clocks were installed at each site, but even these weren't accurate enough alone. New synchronization techniques had to be developed. The data recording systems had to be perfect. Each telescope generates an enormous stream of data, so much that it can't be transmitted electronically. Instead, specially designed hard drives record the signals, marking each data point with ultra-precise timing information. These hard drives are technological marvels themselves. They must write data fast enough to keep up with the incoming signals while maintaining perfect reliability. A single drop bit could corrupt critical observations. Each drive is built to operate flawlessly in extreme conditions. The actual observations require perfect coordination. All telescopes must point at exactly the same spot in the sky at exactly the same time. Consider the precision needed. Telescopes separated by thousands of miles, all focused on a target so distant that it appears smaller than a pinhead on the moon. Weather becomes a cruel master. Clear skies are needed at all sites simultaneously. A single cloudy location can derail an entire observation run. Teams monitor weather patterns constantly, ready to coordinate global observations during brief windows of opportunity. Power systems must be absolutely reliable. A power flicker lasting milliseconds can ruin hours of observation. Each site has multiple backup systems, redundant generators, and power conditioning equipment to ensure pristine electrical supply to sensitive instruments. The human element is just as crucial. Teams at each site must execute complex procedures with perfect timing. They work in shifts, often through the night, maintaining focus despite fatigue and harsh conditions. A single mistake can waste an entire observation session. Communication between sites presents its own challenges. Teams speaking different languages must coordinate complex technical procedures. Time zones complicate scheduling. Cultural differences must be bridged to ensure smooth cooperation. Special equipment monitors atmospheric conditions at each site. Water vapor in the atmosphere can distort or block the faint radio signals. Teams must constantly adjust their observations based on atmospheric conditions, sometimes making split-second decisions to optimize data collection. The signals being captured are incredibly weak. The total energy received from the black hole during months of observation is less than the energy of a single falling snowflake. Detecting these faint signals requires extraordinary measures to eliminate interference. Each site must be protected from radio interference. Cell phones, wireless networks, and even electronic equipment can generate signals that overwhelm the faint cosmic signals. Special shielding and strict protocols protect the sensitive detectors. Transportation of data becomes a critical mission. Hard drives containing precious observations must be physically shipped to central processing facilities. Special containers protect them from temperature extremes, vibration, and magnetic fields that could corrupt the data. The computing infrastructure needed to process all this data is massive. Specialized correlators combine signals from different telescopes, accounting for Earth's rotation, atmospheric effects, and countless other variables. New software had to be written to handle the unprecedented complexity. Each telescope must be maintained in perfect condition. Surface accuracy is critical. Even small deformations from temperature changes or gravity can affect performance. Teams regularly check and adjust the massive structures, ensuring they maintain their precise shape. The project stretches the limits of human organization as much as technology. Hundreds of scientists, engineers, and support staff must work in perfect coordination. Schedules must account for everything from equipment maintenance to human fatigue to weather patterns around the world. This Earth-sized camera represents humanity's most ambitious attempt to peer into the extreme environment around a black hole. It's a testament to human ingenuity, cooperation, and determination to understand our universe. In the heart of the Virgo galaxy cluster, 55 million light-years from Earth, lurks a monster. M87's supermassive black hole became humanity's first target for a reason. This cosmic giant, 6.5 billion times more massive than our Sun, holds secrets that could revolutionize our understanding of the universe. Choosing M87 wasn't a casual decision. Scientists needed a black hole that was massive enough, close enough, and active enough to photograph, despite being millions of light-years away. M87's black hole appears larger in our sky than any other candidate except the one at our galaxy's center. The numbers are staggering. This cosmic titan consumes the equivalent of 2 Earths every day. It launches a jet of particles spanning 5,000 light-years, longer than our entire galaxy. The energy it produces could power civilization for billions of years. Yet all this power emerges from a space smaller than our solar system. M87's jet made it particularly interesting. This stream of particles, shooting nearly at light speed into space, has puzzled astronomers for decades. Photographing the black hole might reveal how these mysterious jets form, solving a century-old astronomical mystery. The black hole's size works in our favor. While Sagittarius A at the center of our galaxy is closer, it's also much smaller and more volatile. M87's supermassive black hole changes slowly enough that it appears relatively stable during observations. It's like photographing a mountain instead of a runner in motion. Its location in space proved crucial. M87 sits at just the right angle for Earth-based telescopes to observe it. The galaxy's orientation gives us a clear view of the black hole's dynamics, unobstructed by intervening gas and dust that could blur our view. The surrounding environment makes it an ideal target. Hot gas swirling around the black hole glows brightly in radio waves, creating a natural backlight. This glowing material helps outline the black hole's shadow, making it possible to see the unseeable. M87's massive scale affects everything around it. The immense gravitational forces create a perfect laboratory for testing Einstein's theories under extreme conditions. Every photon we capture has been warped by gravity more powerful than anything we can create on Earth. The black hole rotates, dragging space-time with it like honey swirling in a jar. This frame-dragging effect influences how matter falls in and how light travels around it. M87's rotation is so powerful it literally twists the fabric of space-time. Time behaves strangely near M87. The gravitational forces are so intense that time moves noticeably slower near the event horizon compared to Earth. What we see as months of activity might be years from the perspective of matter falling into the black hole. The accretion disk tells its own story. This swirls beyond its immediate vicinity. Its gravitational pull affects the motion of stars and gas throughout the galaxy. By studying these effects, scientists can better understand how black holes shape the evolution of entire galaxies. M87's mass isn't static, it's growing. Every year, it consumes enough material to make several new stars. This growth provides clues about how supermassive black holes reach their enormous sizes and continue to evolve over cosmic time. The magnetic fields around M87 are incredibly complex. These fields channel matter into the black hole and help launch the powerful jets into space. Understanding these magnetic structures could reveal how black holes convert mass into energy so efficiently. Radio waves from M87 tell multiple stories. Different wavelengths reveal different aspects of the black hole's environment, from the hot inner accretion disk to the outer regions where jets form. Each wavelength adds another piece to the puzzle. The black hole's shadow, the dark region at its center, is larger than our entire solar system. This shadow isn't just empty space, it's a window into the most extreme physics in the universe, where Einstein's theories meet quantum mechanics. M87's perfect combination of size, distance, and stability made it an ideal first target. Success here would prove the concept and pave the way for observing other black holes, including the one at the center of our own galaxy. This cosmic monster continues to surprise us. Each new observation reveals unexpected details about its behavior and environment. M87 remains a living laboratory for testing our most advanced theories about gravity, space, and time. Science knows no borders. The Event Horizon Telescope collaboration brought together over 200 researchers from 60 institutions across 20 countries. Each brought unique expertise, resources, and perspectives to one of humanity's most ambitious scientific projects. The team structure broke traditional hierarchies. Senior scientists worked alongside graduate students. Theorists collaborated with engineers. Computer scientists joined forces with astronomers. Every voice mattered. Every insight could be crucial. The diversity was unprecedented. Team members came from every continent except Antarctica. They spoke dozens of languages, represented different cultures, and brought varied approaches to problem solving. This diversity proved to be one of the project's greatest strengths. Coordination became an art form. With team members spread across all time zones, someone was always working. Daily video conferences connected researchers worldwide. Decisions required balancing multiple perspectives while maintaining scientific rigor. Cultural differences emerged in unexpected ways. Different countries had different approaches to research, different ways of communicating results, different standards for consensus. The team had to forge new protocols that respected these differences while maintaining scientific standards. Language barriers required creative solutions. English served as the common language, but technical terms often had different meanings in different contexts. Teams developed precise vocabularies to ensure everyone understood exactly what was being discussed. The data analysis teams worked in parallel. Different groups used different approaches to process the same data. This redundancy wasn't inefficient, it was crucial. If multiple teams reached the same conclusions independently, it strengthened confidence in the results. Trust had to be earned and maintained. Each team member needed complete confidence in the work of colleagues they might never meet in person. Rigorous documentation, open sharing of methods, and constant cross-checking became standard practice. Time zones presented constant challenges. When European telescopes were observing, Asian teams were processing previous data while American teams were planning future observations. Every hour of every day, someone somewhere was pushing the project forward. The pressure was intense. The world scientific community was watching. Funding agencies needed results. The media wanted updates. The team had to balance these external pressures while maintaining absolute scientific integrity. Technical expertise flowed across borders. When problems arose at one site, solutions often came from halfway around the world. The constant exchange of ideas and techniques accelerated problem solving and innovation. Young researchers played crucial roles. Their fresh perspectives and willingness to challenge assumptions led to breakthrough solutions. Graduate students often found innovative approaches that veterans hadn't considered. The collaboration extended beyond scientists. Local communities near telescope sites provided crucial support. Government agencies helped navigate international regulations. Universities shared computing resources and facilities. Communication became critically important. Regular updates kept everyone informed of progress, problems, and solutions. Team members learned to share information clearly across cultural and linguistic boundaries. Security was paramount. The project generated massive amounts of sensitive data. Teams developed protocols to share information securely across international boundaries while protecting the integrity of their observations. Personal relationships developed despite physical distances. Team members celebrated each other's successes, supported each other through challenges, shared life events even while focused on the scientific mission. Crisis management became a shared skill. When problems arose, technical failures, weather issues, data corruption, teams across the globe mobilized to find solutions. The project's success depended on this ability to solve problems collaboratively. Knowledge transfer flowed in all directions. Experienced researchers mentored younger scientists. Technical teams shared expertise across sites. Everyone learned from each other, strengthening the entire collaboration. The project changed careers. Young researchers gained unprecedented experience. Senior scientists found new research directions. The collaboration created professional networks that would last lifetimes. Leadership emerged organically. Different aspects of the project needed different kinds of leadership at different times. The structure allowed expertise to guide decision-making rather than traditional hierarchies. Social media played a surprising role. Private channels allowed team members to share quick updates, ask questions, or seek help. These informal communications complemented official project structures. The human element remained crucial. Despite all the technology, successful collaboration depended on trust, respect, and understanding between team members. Personal connections strengthened professional relationships. As the project progressed, the team became more than a collaboration. It became a model for international scientific cooperation, showing how humanity can work together to achieve the seemingly impossible. Time was both enemy and ally in the quest to photograph a black hole. Every observation window was precious, every moment counted, and the pressure to succeed grew with each passing day. The observations required perfect conditions at multiple locations simultaneously. Weather had to be clear at every telescope site. Equipment had to function flawlessly. Even a single point of failure could void entire observation sessions. Each observation window had strict requirements. Water vapor in Earth's atmosphere needed to be minimal. Radio interference had to be at its lowest. The target had to be visible from all participating telescopes. These conditions rarely aligned perfectly. The team monitored weather patterns obsessively. Meteorological data from multiple continents was analyzed constantly. When favorable conditions approached, teams had to mobilize quickly, sometimes with just hours of notice. Every telescope site faced unique challenges. Hawaii's Mauna Kea Observatory dealt with tropical weather systems. Chile's ALMA telescope battled high-altitude winds. Each location required different strategies to maximize observation time. The coordination was intricate. When conditions looked promising, teams worldwide began their preparations. Equipment was checked and rechecked. Backup systems were tested. Everyone had to be ready when the window opened. Time synchronization was critical. Atomic clocks at each site needed constant monitoring. Even microsecond delays could corrupt the data. Teams developed new methods to maintain precise timing across continents. Data recording systems operated at the edge of technological limits. The incoming data stream was massive, pushing storage systems to their maximum capacity. Any disruption meant lost observations that couldn't be recovered. The rotation of Earth added another layer of complexity. As our planet turned, telescopes had to track their target with incredible precision. The timing of observations had to account for this constant motion. Equipment maintenance became a race of its own. Repairs had to be completed between observation windows. Technical teams worked around the clock, knowing that equipment failure during crucial moments could set the project back significantly. The data storage race was equally intense. Each observation session generated petabytes of information. Hard drives had to be transported to processing centers quickly, making way for the next round of observations. Sleep schedules shifted constantly. Teams adapted to irregular hours, staying alert during crucial observation windows regardless of local time. The project demanded extraordinary dedication from everyone involved. Transportation logistics became critical. When weather windows opened, necessary equipment and personnel had to be in place immediately. Travel delays could mean missing rare observation opportunities. Communication channels stayed active 24/7. Updates flowed constantly between sites. Teams shared weather forecasts, equipment status, and observation quality in real time. Every decision affected multiple locations. The pressure of deadlines loomed constantly. Funding agencies expected results. The scientific community waited for findings. Public interest grew, yet rushing the process could compromise the entire project. Data processing teams worked in parallel with observations. Initial analysis had to confirm whether data was usable. Quick feedback helped optimize subsequent observation sessions. Each successful observation was precious. The data represented unique moments in time, capturing the behavior of one of the universe's most extreme environments. Lost opportunities couldn't be recovered. Technical problems required immediate solutions. When issues arose, teams worldwide collaborated to find fixes quickly. The luxury of time wasn't available. Solutions had to work immediately. The psychological pressure was intense. Team members knew they were part of something historic. The weight of potential failure added stress to every decision, every action. Season changes affected planning. Different times of year offered different observation opportunities. The team had to maximize each favorable period while preparing for the next. Backup plans were essential. Multiple scenarios were prepared for every observation session. When primary plans failed, teams switched to alternatives without losing precious time. Equipment upgrades created additional time pressure. New technologies could improve observations, but installing them meant taking telescopes offline. These decisions required careful balancing of risks and benefits. The pace was relentless. As soon as one observation session ended, preparation for the next began. The project demanded constant forward momentum despite obstacles and setbacks. Success required perfect timing at every level, from microsecond telescope synchronization to long-term project planning. The race against time shaped every aspect of the project, pushing human and technological limits to their maximum. Light bends. This simple fact, combined with Einstein's insights about gravity, holds the key to understanding how we can photograph something that swallows light itself. The black hole shadow reveals more than darkness. It tells a story of space, time, and gravity pushed to their absolute limits. What we see in the image isn't the black hole itself, but its effect on surrounding space-time. The dark center represents the event horizon, the point of no return. But it's the bright ring around this darkness that carries the most scientific information. This glowing ring, called the photon ring, is created by light rays that orbit the black hole multiple times before escaping. Some photons circle the black hole once, others circle hundreds of times before breaking free. Each orbit adds information to our image. The asymmetry in the ring's brightness reveals the black hole's rotation. Like water swirling down a drain, space itself gets dragged around by the black hole's spin. This frame-dragging effect makes light brighter on one side of the ring than the other. Temperature plays a crucial role. The gas falling into the black hole heats up to millions of degrees, causing it to glow in radio waves. This superheated material forms an accretion disk, a flattened spiral of gas and dust circling the drain of space-time. Magnetic fields shape the flow of matter. Like invisible force fields, They channel the infalling gas and help launch powerful jets of particles away from the black hole. The image reveals clues about how these magnetic structures work. The size of the shadow confirms Einstein's predictions. General relativity precisely predicts how big the dark region should appear, given the black hole's mass. Our image matches these predictions with unprecedented accuracy. Time behaves strangely near the event horizon. The extreme gravity creates time dilation. Time moves slower closer to the black hole. This effect influences how we observe changes in the infalling material. The image captures radio waves at a specific frequency, chosen to penetrate the gas clouds surrounding the black hole. Like looking through a special filter, this wavelength reveals details that would be invisible in other parts of the electromagnetic spectrum. Quantum effects, while not directly visible, influence what we observe. The boundary between quantum mechanics and gravity lies somewhere near the event horizon. While we can't see this boundary, the image provides clues about how these fundamental forces interact. The resolution achieved in the image represents a technological triumph. The ability to see such fine detail from 55 million light-years away is equivalent to reading a newspaper in New York while sitting in a Paris cafe. Each pixel in the image contains multiple layers of information. Brightness, polarization, and timing data all contribute to our understanding. Scientists can extract different details by analyzing these various aspects of the light. The accretion disk structure reveals fluid dynamics in extreme conditions. The way gas flows around the black hole follows patterns that help us understand how matter behaves under intense gravitational forces. Relativistic effects distort what we see. Light paths are curved so severely that we see multiple images of the same regions overlapped and warped by gravity. Unraveling these distortions requires complex mathematical models. The black hole's mass can be calculated from the image. The size of the shadow, combined with our distance measurements, allows precise determination of the black hole's mass, about 6.5 billion times that of our Sun. Energy conversion processes become visible. The image shows how black holes transform matter into energy with incredible efficiency, converting up to 40% of infalling material into pure energy, far more efficient than nuclear fusion. The sharpness of the shadow's edge provides information about space-time structure. Any fuzziness or irregularities could indicate deviations from Einstein's theories, making this image a test of fundamental physics. Changes in the ring's appearance over time could reveal dynamic processes. Future observations might show how the black hole's environment evolves, providing new insights into high-energy astrophysics. The image also reveals details about the surrounding galaxy. The way the black hole affects its environment helps explain how these cosmic monsters influence galaxy evolution over billions of years. This single image validates decades of theoretical work. Predictions made by physicists and astronomers, some dating back to Einstein's time, are confirmed in stunning detail. The first image of a black hole didn't just show us what one looks like. It opened new frontiers in physics, astronomy, and our understanding of the universe. Each pixel contains data that challenges or confirms theories developed over the past century. Einstein's theories faced their toughest test yet. General relativity predicts exactly how a black hole's shadow should appear. The image matched these predictions with remarkable accuracy, providing the strongest evidence yet for Einstein's description of gravity. The size of the shadow carries crucial information. Its precise measurements confirm our calculations about how space curves around extremely massive objects. This validation extends beyond black holes, supporting our broader understanding of how gravity works throughout the universe. Questions about information loss found new context. The image provides clues about what happens to information that falls into a black hole, one of physics' most perplexing paradoxes. While not resolving the paradox completely, it offers new ways to study this fundamental problem. The behavior of matter under extreme conditions became clearer. We can now observe how gas behaves when subjected to the strongest gravitational fields in the universe. This helps us understand physics in conditions impossible to recreate on Earth. Magnetic field structures around black holes are now better understood. The image reveals how these invisible forces shape the flow of matter and energy near the event horizon. This helps explain the formation of powerful jets that can influence entire galaxies. The connection between black holes and galaxy evolution gained new evidence. Understanding how these cosmic monsters affect their surroundings helps explain how galaxies form and change over billions of years. Quantum gravity theories gained new constraints. The sharp edge of the black hole's shadow helps limit possible variations in how quantum mechanics and gravity might combine at extreme scales. The role of black holes in generating high-energy particles became clearer. The image shows mechanisms that could explain how black holes accelerate particles to nearly the speed of light, producing cosmic rays that reach Earth. Time dilation effects were indirectly observed. The image captures light from regions where time moves at dramatically different rates, providing new ways to study this strange relativistic effect. The efficiency of black holes as cosmic engines was confirmed. The image shows how these objects convert matter into energy with incredible efficiency, far surpassing any process we can create on Earth. Questions about the event horizon's nature found new angles of study. The sharp boundary between light and shadow provides information about the structure of space-time at this crucial boundary. The relationship between black hole spin and jet formation became clearer. Asymmetries in the image help explain how rotating black holes launch powerful jets of particles into space. New methods for studying space-time emerged. The techniques developed to create this image open possibilities for studying other extreme cosmic objects. The limits of our current theories became more apparent. While confirming many predictions, the image also highlights areas where our understanding remains incomplete. The role of turbulence in accretion disks was revealed. The image shows how swirling gas behaves around black holes, helping explain how these cosmic objects feed and grow. Questions about the formation of supermassive black holes gain new context. The detailed view of M87's black hole provides clues about how these giants grew to such enormous sizes. The relationship between visible matter and dark matter near black holes became clearer. The image helps constrain models of how these two forms of matter interact in extreme gravitational fields. The universality of black hole properties was supported. The image suggests that black holes, regardless of their size or location, share fundamental characteristics predicted by theory. New possibilities for testing alternative theories of gravity emerged. The precise measurements allow us to test competing theories of gravity against observational evidence. Models of gas dynamics in extreme conditions gain validation. The image confirms some predictions about how matter behaves near a black hole while challenging others. The role of black holes in cosmic evolution became clearer. Understanding these objects helps explain the structure and development of the universe on the largest scales. The connection between different types of black holes was strengthened. Comparing supermassive black holes with smaller ones helps unify our understanding of these objects. At the heart of our Milky Way lies another monster, Sagittarius A, a supermassive black hole much closer to home than M87. While smaller than its distant cousin, this cosmic neighbor presents unique opportunities and challenges for observation. Just 26,000 light-years away, Sagittarius A is our closest supermassive black hole. Despite its proximity, imaging it proved more challenging than M87. Like trying to photograph a hyperactive child instead of a posed portrait, Sagittarius A changes too quickly for easy observation. The size difference is dramatic. While M87's black hole weighs in at 6.5 billion solar masses, Sagittarius A is relatively modest at 4 million solar masses. Yet this smaller size makes it perfect for studying how black holes affect their immediate surroundings. Our galaxy's black hole is surprisingly quiet. Unlike M87's powerful jets and bright accretion disk, Sagittarius A is relatively dormant. This quietness makes it harder to observe but offers insights into how black holes behave during their rest periods. The view to Sagittarius A is obscured by cosmic dust and gas. Looking toward the galactic center is like peering through a sandstorm. Radio waves must be carefully chosen to penetrate this cosmic haze. Timescales present unique challenges. While M87's enormous size means changes occur over days or weeks, Sagittarius A can transform in minutes. This rapid variation requires different observation and processing techniques. Stars orbiting Sagittarius A provide crucial data. By tracking their precise movements, astronomers can calculate the black hole's mass and behavior. These stellar dancers are our guides to understanding our cosmic neighbor. The feeding patterns differ dramatically from M87. Sagittarius A consumes the equivalent of a large asteroid each day, modest portions compared to M87's diet of 2 Earths daily. This different feeding rate affects everything we observe. Magnetic fields around Sagittarius A create unique patterns. These invisible forces shape the flow of gas and dust, creating complex structures that can change within hours. Understanding these patterns helps explain how black holes interact with their environment. The event horizon of Sagittarius A appears larger in our sky than any other black hole. Despite being smaller than M87's black hole, its relative proximity makes it an ideal target for studying the boundary between normal space and the black hole's interior. Radio emissions from Sagittarius A flicker like a flame. These variations happen so quickly that special techniques are needed to capture them. Each flicker tells a story about how matter behaves in extreme gravitational fields. The environment around Sagittarius A is surprisingly complex. Young stars form dangerously close to the black hole, defying our expectations about what's possible in such extreme conditions. Temperature variations near Sagittarius A provide crucial data. Gas temperatures can spike from millions to billions of degrees in moments, revealing how black holes heat their surroundings. The rotation of Sagittarius A affects everything nearby. Space itself gets dragged around by the spinning black hole, creating conditions impossible to replicate in any laboratory. Studying Sagittarius A helps us understand galaxy evolution. As a relatively quiet black hole, it shows how these objects behave during their dormant phases, which comprise most of their existence. The impact on surrounding gas clouds reveals new physics. As material falls towards Sagittarius A, it behaves in ways that challenge our understanding of fluid dynamics and plasma physics. Regular flares from Sagittarius A provide natural experiments. These bright outbursts let us track how material moves in the extreme environment near a black hole's event horizon. Distance measurements to Sagittarius A help calibrate our cosmic scales. Having a precise distance to the galactic center improves our understanding of the Milky Way structure and evolution. Future observations promise new discoveries. As technology improves, we'll be able to study faster changes and smaller details around Sagittarius A, revealing more about these cosmic enigmas. Our galactic center serves as a laboratory for extreme physics. Sagittarius A lets us study gravity, magnetism, and plasma behavior in conditions impossible to create on Earth. Photographing a black hole wasn't just a triumph of physics, it was a masterpiece of engineering. The technical innovations required pushed the boundaries of what humans thought possible, creating new technologies that will benefit science for decades to come. The data recording systems broke all previous records. Each telescope site needed to capture information at rates exceeding what the fastest internet connections could handle. Engineers developed new hard drive systems that could write data faster than ever before. Atomic clock synchronization reached new levels of precision. Teams developed methods to keep multiple telescopes synchronized to within a fraction of a billionth of a second. This timing accuracy was crucial for combining data from different locations. The signal processing algorithms represented a quantum leap in capability. Traditional methods couldn't handle the complexity of the data. Computer scientists created new ways to extract signals from noise, pushing the boundaries of what we could detect. Weather prediction for the project required unprecedented accuracy. New models were developed to predict atmospheric conditions at multiple sites simultaneously. These improvements in weather forecasting now benefit other scientific projects. Computing power reached new scales. Processing the black hole data required supercomputers working at their limits. Teams developed new ways to parallel process information, advancing our ability to handle massive datasets. The telescope pointing systems achieved incredible precision. Despite operating in harsh conditions, the telescopes maintained accuracy equivalent to hitting a quarter in Los Angeles with a laser pointer in New York. Data storage technology evolved to meet the challenge. New methods for storing and transferring massive amounts of information were developed. These advances now help other big data projects in science and industry. The radio receivers pushed sensitivity limits. Engineers developed ways to detect incredibly faint signals, advancing our ability to observe distant cosmic objects. These improvements benefit all radio astronomy. Image reconstruction software broke new ground. Teams created algorithms that could build pictures from incomplete data, advancing fields from medical imaging to satellite photography. The calibration system set new standards. Methods for ensuring data accuracy across multiple instruments advanced our ability to conduct precise scientific measurements. Network coordination software evolved rapidly. New tools for managing global scientific collaborations were developed, benefiting other international research projects. Temperature control systems maintained incredible stability. Despite extreme environmental conditions, sensitive equipment was kept at precise temperatures, advancing our ability to operate in harsh environments. Power supply systems achieved new levels of reliability. Engineers developed ways to provide clean, stable power in remote locations, benefiting other scientific installations worldwide. The data verification systems broke new ground. Methods for ensuring data integrity across global networks advanced our ability to conduct precise long-distance measurements. Signal filtering technology reached new levels. Teams developed better ways to remove interference from observations, improving all forms of radio astronomy. The telescope surface accuracy set new standards. Methods for maintaining large structures with sub-millimeter precision advanced our engineering capabilities. Transportation systems for sensitive equipment improved. New methods for shipping delicate scientific instruments now benefit other global research projects. Communication systems bridged global divides. Tools for coordinating complex operations across continents advanced our ability to conduct international science. Quality control systems evolved rapidly. New methods for ensuring consistent results across multiple sites advanced all forms of distributed scientific research. Signal filtering technology reached new levels. Teams developed better ways to remove interference from observations, improving all forms of radio astronomy. The telescope surface accuracy set new standards. Methods for maintaining large structures with sub-millimeter precision advanced our engineering capabilities. Transportation systems for sensitive equipment improved. New methods for shipping delicate scientific instruments now benefit other global research projects. Communication systems bridged global divides. Tools for coordinating complex operations across continents advanced our ability to conduct international science. Quality control systems evolved rapidly. New methods for ensuring consistent results across multiple sites advanced all forms of distributed scientific research. These advances represent more than just a single achievement in astronomy. They mark a fundamental leap forward in human technical capability, opening doors to new possibilities across all scientific endeavors. As we push the boundaries of what's possible, each breakthrough builds the foundation for the next discovery. Great scientific achievements are human achievements. Behind every equation, every line of code, every observation, stood people driven by an unquenchable curiosity about the universe. Their stories are as remarkable as the discovery itself. Early mornings and late nights became routine. In observatories perched on remote mountaintops, scientists and engineers worked through exhaustion, knowing they were part of something historic. Some spent weeks away from their families, missing birthdays, anniversaries, and holidays. The collaboration crossed generations. Veteran scientists who had spent decades studying black holes worked alongside young graduates, experiencing their first major research project. Fresh perspectives mixed with years of experience, creating a unique dynamic that drove innovation. The pressure was immense. Every team member knew the world was watching. Equipment failures, bad weather, and technical glitches became personal battles. Success required not just scientific expertise, but extraordinary persistence. At high-altitude observatories, technicians worked in extreme conditions. The thin air made every task more challenging. Simple maintenance jobs became endurance tests, yet they persevered, knowing their work was crucial to the project's success. Computer scientists faced their own challenges. Processing the massive amounts of data required new approaches. They worked around the clock, developing and testing algorithms that could extract meaning from the noise of space. In university laboratories, graduate students tackled complex problems that had stumped experts for years. Many made crucial breakthroughs, their fresh approaches leading to new technical issues. Science became their common language. Cultural differences enriched the collaboration. Different approaches to problem solving, different ways of thinking, different working styles, all contributed to the project's success. The diversity of perspectives proved invaluable. Family sacrifices were significant. Team members missed important moments with loved ones. Children grew used to video calls with parents working at distant observatories. Partners and spouses provided crucial support throughout the long journey. The emotional investment was intense. Years of work could be jeopardized by a single mistake. The responsibility weighed heavily on every team member. Yet this pressure forged strong bonds between colleagues. Leadership emerged at all levels. Junior team members showed initiative in solving critical problems. Veterans stepped back when others had better solutions. Traditional hierarchies gave way to expertise and ability. The project changed lives beyond science. Friendships formed across continents. Career paths shifted. Personal growth accompanied scientific achievement. Many found themselves capable of more than they had imagined. Health challenges tested determination. Working at high altitudes affected physical well-being. Irregular schedules disrupted sleep patterns. Mental stress took its toll. Yet the team's commitment never wavered. Moments of doubt were inevitable, when problems seemed insurmountable, when deadlines loomed impossible, when nature itself seemed to conspire against success. The team's shared vision kept them going. Celebration and disappointment often came together. Successful observations could be followed by equipment failures. Breakthrough moments were tempered by new challenges. The team learned to maintain focus through ups and downs. Personal rivalries gave way to collaboration. The scope of the challenge demanded cooperation. Individual ambitions merged into collective achievement. The team recognized that success required everyone's best efforts. Recognition came in unexpected ways. Local communities near observatories took pride in their role. Students were inspired to pursue science careers. The public became engaged with fundamental physics in new ways. The human story behind the discovery reminds us that science is not just about technology and data. It's about people pushing boundaries, overcoming challenges, and working together to achieve the seemingly impossible. The first image of a black hole didn't just make headlines, it revolutionized astrophysics. This single picture changed how we study the universe, opening new avenues of research and challenging our understanding of cosmic phenomena. Traditional theories faced their ultimate test. For decades, scientists had predicted what a black hole should look like. The image confirmed some theories while forcing us to reconsider others. Every pixel contained information that could validate or challenge our understanding. Our understanding of jet formation evolved dramatically. The image revealed crucial details about how black holes launch powerful streams of particles into space. These jets, which can span thousands of light years, influence the evolution of entire galaxies. The role of magnetic fields gained new importance. The image showed how invisible magnetic forces shape the flow of matter around black holes. This understanding helps explain everything from solar flares to distant quasars. Questions about information loss found new context. The sharp boundary between light and shadow provided clues about what happens to information that falls into a black hole. This fundamental puzzle of physics gained new avenues for investigation. The relationship between black holes and their host galaxies became clearer. Understanding how these cosmic monsters influence their surroundings helps explain galaxy formation and evolution throughout the universe. New tools for studying extreme gravity emerged. The techniques developed for imaging M87's black hole now help us study other objects where gravity reaches extraordinary strengths. The nature of space-time near black holes came into focus. The image revealed how space and time behave in the strongest gravitational fields in the universe, providing tests for theories about the fabric of reality. Our ability to measure black hole masses improved. The precise measurements from the image enhanced our understanding of how to weigh these invisible objects, improving our cosmic senses. The role of black holes in galaxy evolution gained clarity. Seeing how matter behaves near the event horizon helps explain how black holes influence their galaxies over billions of years. Time dilation effects became more tangible. The image captured light from regions where time moves at dramatically different rates, providing new ways to study this relativistic phenomenon. Questions about event horizon structure found new angles of study. The sharp boundary in the image helped constrain theories about what happens at the edge of a black hole. The efficiency of cosmic engines was confirmed. The image showed how black holes convert matter into energy with incredible efficiency, far surpassing any process we can create on Earth. Our understanding of accretion processes deepened. Seeing how matter falls into a black hole provided crucial insights into how these objects grow and influence their surroundings. The limits of our current theories became more apparent. While confirming many predictions, the image also highlighted areas where our understanding remains incomplete. New possibilities for studying quantum gravity emerged. The sharp edge of the black hole's shadow provided constraints on theories attempting to unite quantum mechanics and gravity. Our grasp of extreme physics expanded. The image revealed how matter behaves in conditions impossible to recreate on Earth, advancing our understanding of fundamental physics. The universality of black hole properties was tested. Comparing the image with theoretical predictions helped confirm that black holes, regardless of size, share fundamental characteristics. Our ability to study cosmic evolution improved. Understanding black holes helps explain how the universe developed its current structure and what its future might hold. The connection between theory and observation strengthened. The image provided a crucial bridge between mathematical predictions and observable reality, advancing our ability to test cosmic theories. The first black hole image was just the beginning. As technology advances and techniques improve, our view of these cosmic monsters will become clearer, sharper, and more revealing. The future holds promises of discoveries we can barely imagine. New telescopes will join the network. Each additional observatory improves resolution and sensitivity. Sites are being developed from Antarctica to space, creating an even larger virtual telescope. Higher frequencies will reveal new details. Future observations will use shorter wavelengths of light, providing sharper images of the black hole's environment. This will show features currently too small to see. Computing power continues to grow. More powerful processors will handle larger amounts of data faster, allowing more sophisticated analysis. Artificial intelligence will find patterns humans might miss. Real-time imaging is coming. Instead of waiting months for data processing, future systems will show black hole activity as it happens. We'll watch cosmic events unfold before our eyes. Weather prediction will improve. Better forecasting will help coordinate observations across global sites. More observation windows mean more opportunities for discovery. Faster data transfer will speed analysis. New methods for handling massive datasets will reduce the time between observation and discovery. Results that took months might take days. Space-based telescopes will eliminate atmosphere problems. Observatories above Earth's atmosphere will provide clearer views. These will work together with ground-based telescopes for unprecedented detail. Multiple black holes will be imaged. After M87 and Sagittarius A, other targets await. Each new black hole studied adds to our understanding of these cosmic phenomena. Time-lapse observations will show evolution. We'll watch how black holes change over days, months, and years. This will reveal dynamic processes never before seen. Resolution will increase dramatically. Sharper images will show finer details around the event horizon. Features now blurred will become distinct. Three-dimensional views will emerge. By combining different types of observations, we'll build 3D models of black hole environments. This will reveal their true structure. New wavelengths will add information. Observations across more of the electromagnetic spectrum will provide a complete picture of black hole physics. Magnetic field mapping will improve. Better measurements of magnetic forces around black holes will explain jet formation and matter flow. Coordination between facilities will increase. More observatories working together means better coverage and more detailed observations. Signal processing will become more sophisticated. New algorithms will extract more information from observations. Details once lost in noise will become visible. Polarization measurements will advance. Better understanding of light polarization around black holes will reveal hidden structures. Timing accuracy will increase. More precise synchronization between telescopes will allow detection of faster changes. Error correction will improve. Better methods for handling data problems will produce clearer, more reliable images. The connection between observation and theory will strengthen. Each improvement in imaging will test theoretical predictions more precisely. As these improvements arrive, our understanding of black holes will deepen. Each advance brings new questions, new mysteries, and new opportunities for discovery. These developments represent more than technical progress. They open windows into the fundamental nature of our universe. The future of black hole imaging promises to reveal secrets we're only beginning to imagine. The future of black hole observation goes far beyond still photographs. Scientists are working to create movies of black holes in action, showing these cosmic monsters as they feed, spin, and shape the space around them. Dynamic imaging will reveal new physics. Instead of snapshots, we'll watch matter swirl around the event horizon in real time. These observations will show how black holes interact with their environment moment by moment. The accretion disk dance will come alive. We'll observe how gas and dust spiral inward, heating up as they approach the point of no return. This cosmic ballet will help explain how black holes grow and influence their surroundings. Jet formation will be captured in action. For the first time, we'll watch as black holes launch powerful streams of particles into space. These observations will solve long-standing mysteries about how these jets form and evolve. Magnetic field behavior will become visible. We'll see how invisible magnetic forces shape the flow of matter around black holes. These dynamics play crucial roles in everything from jet formation to energy release. Time variations will reveal new patterns. Some changes happen in minutes, others over months or years. Capturing these different timescales will show how black holes behave across different periods. Multiple wavelength movies will combine data. By synchronizing observations across different parts of the electromagnetic spectrum, we'll build complete pictures of black hole activity. Flare events will be recorded as they happen. Sudden bursts of energy from near the event horizon will show how black holes convert matter into energy with incredible efficiency. Temperature changes will be tracked over time. We'll watch as matter heats to millions of degrees during its final plunge toward the black hole, revealing extreme physics in action. The shadows dance will be revealed. The black hole's silhouette might wobble or change shape as conditions around it evolve, testing our theories about space-time behavior. Orbital dynamics will become clear. We'll track how matter moves in the extreme gravitational field near a black hole, providing new tests of Einstein's theories. Space-time distortions will be captured. The way black holes bend light will be shown in unprecedented detail, revealing how gravity warps the fabric of space itself. Matter destruction will be witnessed. We'll observe the final moments as material crosses the event horizon, providing clues about what happens at this crucial boundary. Energy conversion will be seen in action. These movies will show how black holes transform matter into pure energy more efficiently than any other process in the universe. Binary black hole interactions might be captured. If we're fortunate, we might even observe two black holes as they orbit each other and eventually merge. Relativistic effects will become apparent. Time dilation and other consequences of Einstein's theories will be demonstrated in clear visual ways. Long-term evolution will be documented. Over years of observation, we'll see how black holes grow and change, improving our understanding of galactic evolution. New phenomena might be discovered. Moving images might reveal unexpected behaviors or features that static photographs couldn't capture. Interactive visualizations will enhance understanding. Scientists will be able to examine black hole behavior from multiple angles and perspectives. The public impact will be revolutionary. These dynamic views will transform how people understand and appreciate these cosmic wonders. The black hole image didn't just advance science, it transformed how we teach and learn about the universe. From elementary schools to universities, this visual evidence of Einstein's theories revolutionized science education. Before the image, black holes lived in imagination and equations. Teachers relied on analogies and drawings to explain these cosmic phenomena. Now, they can show students the real thing, making abstract concepts tangible. Students' understanding of gravity changed dramatically. The image provided clear evidence of how space bends around massive objects. Complex physics became accessible through this single, powerful visualization. The public's engagement with science soared. People who had never thought about astrophysics found themselves fascinated by black holes. The image sparked curiosity about the cosmos across all age groups. Classroom discussions gained new depth. Teachers could now lead conversations about direct evidence rather than theoretical predictions. Students could see for themselves what scientists had only imagined for decades. Textbooks underwent rapid revision. Publishers rushed to include the image and its implications. The way we teach about gravity, space, and time evolved to incorporate this new evidence. Online education resources multiplied. Interactive tools helped explain what the image showed. Virtual simulations let students explore black hole physics in new ways. Science fairs saw an explosion of black hole projects. Young students tackled complex physics concepts with newfound confidence. The image provided a foundation for understanding cosmic phenomena. University curricula expanded. New courses focused on the techniques used to capture the image. Students learned about radio astronomy, data processing, and global scientific collaboration. Laboratory exercises evolved. Physics classes developed new experiments to demonstrate principles revealed by the image. Engineering students studied the technical achievements behind the discovery. Distance learning benefited enormously. The image provided a common reference point for students worldwide. Online discussions could focus on real observations rather than theoretical models. STEM education gained new momentum. The achievement inspired students to pursue careers in science and technology. The human story behind the discovery showed science as an exciting, collaborative endeavor. Art and science found new connections. The image's aesthetic beauty demonstrated how scientific truth can also be visually stunning. Cross-disciplinary learning took on new dimensions. Global perspective in education strengthened. Students learned how scientists from different countries work together. The project became a model for international cooperation. Critical thinking skills improved. Students learned to analyze complex data and evaluate scientific evidence. The image provided opportunities to discuss how we know what we know. Public understanding of scientific research deepened. People gained insight into how major discoveries happen. The years of effort behind the image showed science as a process, not just results. Scientific literacy advanced. Complex concepts like gravity, space-time, and electromagnetic radiation became more approachable. The public gained better tools for understanding cosmic phenomena. Future generations gained inspiration. Young people saw proof that seemingly impossible goals can be achieved. The discovery showed how human curiosity and determination can reveal universe's deepest secrets. Educational technology adapted rapidly. New tools and applications helped explain the discovery. Interactive media made complex physics accessible to broader audiences. The legacy continues in classrooms today. Each new student who sees the image experiences the thrill of viewing what Einstein only imagined. Education will never be the same. The black hole image transcended science, becoming a cultural phenomenon that changed how humanity sees its place in the universe. This single picture sparked conversations not just in laboratories, but in homes, coffee shops, and social media across the globe. The moment of revelation captured global attention. News broadcasts worldwide interrupted regular programming. Social media erupted with discussion. For a brief moment, humanity united in collective awe at what we had achieved. Artists found new inspiration. The image's mysterious beauty sparked creative interpretations across all media. Paintings, sculptures, music, and poetry explored what it meant to finally see the unseeable. Popular culture embraced the discovery. Movies and television shows rushed to incorporate accurate black hole representations. Science fiction writers found new material in reality stranger than imagination. The public's relationship with science evolved. Complex physics became dinner table conversation. People who had never thought deeply about the cosmos found themselves pondering gravity and space-time. Social media played a unique role. The image spread instantly across platforms, accompanied by explanations ranging from simple to profound. Scientific discussions reached audiences that traditional channels never could. The human story resonated deeply. People connected with the scientists' dedication, the years of effort, the global collaboration. It became a story of human achievement as much as scientific discovery. Philosophy and science intersected in new ways. The image raised questions about humanity's place in the cosmos. Discussions about existence, reality, and our role in the universe gained new context. Religious and scientific perspectives found common ground. The image's beauty inspired awe across belief systems. It became a reminder of the wonder that unites human experience. Education transformed at all levels. Children drew black holes in art class while discussing gravity and science. The image bridged disciplines, showing how art and science complement each other. Media coverage evolved with the story. Journalists learned to explain complex physics to general audiences. Science communication found new ways to engage the public. The digital age showed its power. The images released demonstrated how scientific news spreads in modern times. Traditional media and social platforms worked together to share the discovery. Global perspectives emerged naturally. Different cultures interpreted the image through their own lenses. The universal nature of scientific discovery bridged cultural divides. Future generations gained a new reference point. Like the first moon landing, this moment marked a shift in human capability. It showed what we can achieve when we work together. Tourism at observatories increased dramatically. People wanted to see the facilities that made the discovery possible. Science tourism gained new popularity. The public's trust in science strengthened. The accurate predictions of Einstein's theories, confirmed by the image, showed the power of scientific method. Environmental awareness grew unexpectedly. The image reminded people of our cosmic context and Earth's uniqueness. Discussions about preserving our planet gained new urgency. International cooperation gained a powerful example. The project showed how global collaboration could achieve seemingly impossible goals. Political boundaries faded against scientific achievement. Local communities near observatories felt pride. Their role in the discovery brought recognition to remote locations. Science connected global and local perspectives. The impact continues to ripple through society. Each new generation discovers the image for the first time. Its influence on human culture grows with every passing year. The first black hole image opened doors to new scientific frontiers. What began as a quest to photograph the unseeable has evolved into multiple research paths that promise to revolutionize our understanding of the universe. Time-lapse imaging heads the list of priorities. Scientists are working to create movies of black holes in action. These dynamic views will show how matter moves near the event horizon, how jets form, and how black holes shape their environment. More black holes await their close-up. Each new target will reveal different aspects of these cosmic monsters. Comparing different black holes will help us understand what features are universal and what varies. Higher resolution images are coming. New telescopes, better algorithms, and improved technology will sharpen our view. Details currently hidden will become clear, testing theories about black hole physics. The connection between black holes and galaxy evolution needs exploration. Understanding how these cosmic giants influence their surroundings will explain how galaxies form and change over billions of years. Quantum gravity might find its first observational tests. The sharp edge between light and shadow in black hole images could reveal where Einstein's physics meets quantum mechanics. Multiple wavelength observations will build complete pictures. By combining different types of light, radio, infrared, X-ray, scientists will create comprehensive views of black hole environments. Magnetic field mapping will improve dramatically. Better understanding of magnetic forces around black holes will explain jet formation and energy flows. Einstein's theories face more stringent tests. Each new observation challenges general relativity in stronger ways. Any tiny deviation could point toward new physics. Binary black hole studies will expand. Observing two black holes orbiting each other could reveal new aspects of gravity and space-time behavior. The mystery of information loss needs resolution. Better observations near the event horizon might help solve this fundamental puzzle of physics. Accretion disk physics requires deeper study. Understanding how matter falls into black holes will explain energy production in these cosmic engines. Dark matter's role near black holes demands investigation. These extreme environments might reveal new properties of this mysterious substance. Space-based observations will complement ground telescopes. Removing atmospheric interference will provide clearer views and new perspectives. Gravitational wave observations will merge with imaging. Combining these different messengers will provide new insights into black hole behavior. Faster-than-light travel possibilities need exploration. Understanding the extreme warping of space-time might reveal ways to navigate the cosmos. The role of black holes in early universe evolution requires study. These objects might explain how the first galaxies formed and grew. Computer simulations will become more sophisticated. Better models will help us understand what we observe and predict what to look for. The search for wormholes might gain new tools. If these theoretical tunnels through space-time exist, improved imaging might find them. Ultimately, these research directions might reveal new physics beyond our current theories. Each step forward opens new questions, new mysteries, and new possibilities. Our journey through the first black hole image has revealed an incredible story of human achievement, scientific breakthrough, and cosmic wonder. But this is just one of many fascinating stories from our universe. Join us next time as we explore more cosmic mysteries, from the birth of stars to the death of galaxies. Make sure to subscribe and hit the notification bell to never miss our upcoming adventures into space, time, and the greatest discoveries of human history. Until then, keep looking up. The universe is full of wonders waiting to be discovered.